Machine Learning, a Practitioner's Approach Lecture Number 4, Supervised and Unsupervised Learning. This chapter discusses the introductory remarks of supervised and unsupervised learning in machine learning. The following chapters discussed the details of each technique with examples and case studies. Suppose we have two datasets A and B containing some medical image data which transmit the disease information of an organ. We know the labels of all data in the dataset A, that is, whether one image represents diseased or not. But the images in dataset B are not labeled, that is, we do not know whether the organ is diseased or not. How do we classify the images in second dataset B? In this case, we can build a classification model using the dataset A, since all images are labeled as diseased or not. After fine-tuning the model, we can use this model to classify the data in dataset B, since the data are not labeled before. This classification model is built by supervised learning techniques. Here dataset A is called training dataset and B is called testing dataset. Suppose we do not know the labels of both datasets A and B. How do we group the data in A and B in diseased class or not? Using unsupervised techniques, we can group the data in set A and B. Usually, supervised techniques are used for classification or prediction and regression problems. Unsupervised techniques are used in dimensionality reduction and clustering problems. Learning is the process of acquiring knowledge. As mentioned in earlier chapters, we have basically three types of learning: supervised, unsupervised, and reinforcement learning. In addition to these three techniques, evolutionary learning techniques also evolved in the machine learning. Major difference between supervised and unsupervised learning is illustrated in figure. This cartoon gives the difference in human learning process. A training sample set with correct responses are provided. Based on this training set, the algorithm generalizes to respond correctly to all possible inputs. Supervised learning or classification can be normally employed in situations where the training data are fully available. In cases where the part of data is hidden or missing, this type of learning will fail. The labeling of data is done by an expert. For example, positive and negative data are given and are counted as a datasets of shapes. These data are a mix of positive and negative items with a set of properties. Here color, shape and size are these properties. From this dataset, first we have to identify the parameters from the properties like color, shape and size of the given shapes. In the next step, we have to label the item parameters into blue, red, torus, square, star, arrow, big, and small. Now, we have three parameter sets, say, x1, x2, x3. There are two parameters in x1, four parameters in x2 and two parameters in x3. We need to classify whether an item can be selected or not. That is yes or no. Hence, the output is either in Y or N. In this case, we have to prepare a separate training dataset and test dataset. Generalization is the key issue of supervised learning. There are many techniques in supervised learning. Supervised learning successful applications are face detection, steering an autonomous car, detecting credit card fraud, medical diagnosis, sound detection, language identification, and many more. The unsupervised learning process is independent, where training instances organize themselves and form clusters. This is analogous to the case of a baby bird when grown up and feathers developed, explores the world on its own. Unsupervised learning uncovers previously unknown pattern of data. Most of the time, these data patterns are poor approximations and the outcome is unpredictable. There are many techniques in unsupervised learning. In the training set of unsupervised learning, target class information is not required. Once the model is trained, and a new input pattern is applied, output response indicates the class which the pattern belongs to. When we have no desired outcome on the input dataset, unsupervised learning is very suitable. For example, to understand the better market from the existing consumer base, Supervised learning is good. But to determine the target market for a new product that is not sold before, unsupervised learning technique is good. The unsupervised learning techniques are shown here. The supervised or unsupervised method selection is based on the availability of class information on training examples. These aspects are required to consider while designing a machine learning model. The model design is based on the data types as we required to select. Machine learning systems spread over as classifiers or predictors. The output of the machine learning system is to be designed for the purpose of an input dataset. These datasets contain positives and negative examples. There is a classification rule like: if example satisfies condition, then assign it to class X. In the above example, X is either birds or non-birds. In this cartoon, you can see the difference between supervised and unsupervised learning techniques. Here Bagheera acts as a teacher for the supervised learning. This type of learning falls between supervised learning and unsupervised learning. The algorithm gets intimated when there is incorrect answer, but fails to get intimated how to correct it. It has to explore and try out different possibilities to get the correct response. That is, the learning process is outcome-based. How do we practice bicycle riding? Is it supervised or unsupervised learning, in which we examine how a person can learn from success and failure, reward and punishment? The reinforcement learning helps a person to ride bicycle without falling over. Riding bicycle and performing a series of actions results in bicycle being tilted 45 degrees to the right. Suddenly turning of the handlebar left or right crashes the system. In reinforcement learning, system has learned that the state of bicycle being tilted 45 degrees to the right is bad. To repeat trial using 40 degrees to the right and by performing enough of these trial and error interactions with the environment, the reinforcement system will ultimately learn how to prevent bicycle from ever falling over. The principle of biological evolution by survival of the fittest theory is modeled as a learning process in this type of learning. Based on the fitness and survival rates of data, the algorithm responds with a score that measures the goodness of current solution. The model can be built in either supervised or unsupervised terminology. Initial experiments are conducted and fed into the designed model, but this model may not be good enough to predict best results. A redefined process on the parameters and model components improve the performance of designed model. The dataset is incorporated into the model configuration for making a perfect model. It is not a good practice to use the same dataset as used for testing purposes also used for the validation process. The distribution of training, testing and validation dataset distribution is given in figure. Cross-validation is a rotation estimation or out-of-sample testing technique for a machine learning model with a test process by statistically independent dataset. It is used to estimate how accurately a predictive model performed in practice. Major goal of the cross-validation is to test the model's ability to predict data that was not used in estimating. In the k-fold validation, a single parameter called k, which refers to the number of splits in a dataset that is used for training and testing process. If we choose k equals 10, then a 10-fold cross-validation is applied into the machine learning model. Figure shows 10-fold cross-validation cycles. During the training process, the actual output from the model is compared with desired output and error is fed back to the model. This error signal is used to adjust parameters of the model, and this process repeats until the system converges. In figure, positive and negative data are given and are counted as a data sets of shapes. These data are a mix of positive, select, and negative items with a set of properties. That is, color, shape and size. From this dataset, first we have to identify the parameters from the properties like color, shape and size of the given shapes. In the next step, we have to label the item parameters into blue, red, torus, square, star, arrow, big, small. Now, we have three parameter sets, say, x1, x2, x3, There are 2 parameters in x1, 4 parameters in x2 and 2 parameters in x3. We need to classify whether an item can be selected or not. Hence, the output is either in Y or N. In this case, we have to prepare a separate training dataset and test dataset. Figure shows the corresponding supervised learning technique designed for this scenario. Here, we have to formulate a hypothesis, obtained from the designed learner. The prediction from test dataset is done by the learner using hypothesis. Note that the parameters are reassigned numeric or different letters. To understand the supervised learning terminology for the above case, assign a letter of each parameter like first letter in most of the parameters. The bias-variance trade-off is related to model generalization. There should be a balance between bias and variance. The term bias deals with constant error term and variance deals with the amount by which the error may vary between different training sets. Note that these two terms move in opposite directions to each other. That is, when bias increases, variance decreases. Based on the specific nature of the training dataset, make a convenient bias-variance spectrum. In certain tasks to achieve a guaranteed baseline level of performance, we can choose increasing bias and automatically decreasing variance. Small and simple dataset is usually learned by low variance models. The complex or large dataset requires high variance models to learn the structure of data completely. The trade-off between biased and variance is given in figure. An optimal point is reached with a specific bias and variance in the dataset. At this point, there should not be underfit or overfit conditions met. The way of selecting a model in supervised learning can be obtained from these conditions. It can be a classification problem with two classes with real valued or discrete input variables. Since there are only two classes in this problem, it can be treated as a binary classifier. The output probability of the prediction system decides whether an email is a spam or not while arriving to the inbox. For example, probabilities of 0.1 as being spam and 0.9 as being non-spam. The response category value comes into classes like yes or no is basically included in binary classifier. In multi-class classification, more than one group is required to predict. Consider a small dataset given in figure A. The three parameters are name, rank and years of service. We have to predict if a person is tenured or not. In this case, parameter name does not have any importance, but other two parameters contribute to the prediction process. Figure B shows how the prediction is done for the test dataset and an unseen data. Here we can use a regression function that will work as a prediction function. The unsupervised learning process is independent, where training instances organize themselves and form clusters. This is analogous to the case of a baby bird when grown up and feathers developed, explores the world on its own. In the training set of unsupervised learning, target class information is not required. Once the model is trained, and a new input pattern is applied, output response indicates the class which the pattern belongs to. For example, figure gives a mixture of images that contain birds and non-birds. An unsupervised technique like clustering groups these images into two classes like birds and non-birds. Clustering, representation learning and density estimation are most common tasks done by unsupervised learning. There is no label available that has an inherent structure in the available data while an unsupervised learning model is selected. Because of this reason, the performance comparison of unsupervised learning is difficult. Data compression is used to make the dataset as small and efficient as possible by using algorithms on dataset with lesser training. This process is called dimensionality reduction that comes in unsupervised learning category. The principal component analysis finds the linear combinations that communicate most of the variance in a data. It is a statistical procedure to label a set of multivariate data. The labeling is done by correlation of variables by relatively few numbers of linearly uncorrelated variables. If the training dataset is explained by multiple characteristics, Principal component analysis summarizes the characteristics of the dataset and explains the dataset correctly. It removes the redundancy or correlation when explain the data, if a large number of variables in the dataset that are uncorrelated. The major issues in unsupervised learning is evaluation. For example, the clustering technique needs internal and external evaluations. There are problems while applying clustering techniques like overlapping clustering, ensemble clustering, clustering structured relational data. When we select semi-supervised method, the unsupervised technique has some problems. The human learning is from labeled and unlabeled data. So, we can say that the human learning is semi-supervised. Semi-supervised learning is a class of machine learning technique that uses small quantity of labeled data with large quantity of unlabeled data for the training. Semi-supervised learning falls between supervised and unsupervised learning techniques. Using the mixture of labeled and unlabeled data for training is cost-effective and produces good results. The techniques are self-training, co-training, generative methods, graph-based methods, semi-supervised SVM. Train classifier on labeled data and use classifier to classify unlabeled data. Add predicted unlabeled data with high confidence to training set followed by retraining the classifier. There are certain assumptions made for this training. The features can be split into two sets. Each sub-feature set is enough to train a classifier and sub-feature sets are conditionally independent in the class. Two classifiers are trained by using the sub-feature sets of the labeled data and then classifying unlabeled data using each classifier. Using the predicted labels of the unlabeled data, each classifier trains the other classifier. Generative models are a semi-supervised method that identifies mixture components. Types of generative models are Gaussian mixture model, hidden Markov model, probabilistic context-free grammar, Bayesian network, average one dependence estimators, latent Dirichlet allocation, Boltzmann machine, variation autoencoder, generative adversarial network and flow-based generative model. Basic idea is to construct a graph connecting similar data points. The intuition is that similar data points have similar labels and the information propagates from labeled data points. A basic assumption of this method is that similar unlabeled data have similar labels. The similarity in the graphs develops a local neighborhood relation between data points. Transductive SVMs is called semi-supervised support vector machines or SIVM optimize over both margin and labels of unlabeled points, instead of finding maximum margin between labeled points. Basic assumption of this SVM is unlabeled data from different classes separated with large margin. In SIVM, unlabeled data guides the linear boundary away from thick regions, hence the classification is better than SVM. Figure gives a comparison of supervised and unsupervised learning methods over a continuous and discrete dataset. The supervised learning model performs as a prediction/classification technique in a continuous dataset. For example, SVM and multi-layer perceptron perform as a classifier on continuous dataset. A comparison of supervised and unsupervised method is given in figure. The predictive model and the machine learning algorithm are different based on the problem selected. If the data is not labeled, then unsupervised learning techniques can be adapted to solve a problem. In a supervised technology, the expected labels are predicted, but in unsupervised learning, the clusters are formulated or better representation suggestion is given. There are certain differences in supervised and unsupervised learning techniques. Table shows these differences based on the selected features listed in the first column. Based on the decision, one can select any algorithm that belongs to either supervised or unsupervised paradigm. You may please check the case studies discussed in this chapter. The case studies are learning engine for process power plants, elephants identification and retail analysis. Please check the exercises for your self-improvements.